Today's lecture is on trigonometric integrals. As we are done with chapter 5, at this point we know a large collection of techniques for computing the definite and the indefinite integrals. Well, in these lectures, what we are going to do is collect all these methods together and apply them to a particular class of integrals involving the trigonometric integrands. like we'll consider three families of integrals involving the trigonometric functions. The first one is the power of sine and cos. The second one is the power of tangent and sorry. The second one is the power of tangent and secant, and the third one and in the third comes the multiples of sines and cosines. So throughout m and n are going to denote the positive integers. For our first class of integrals, consider an integrand sine raised to the power mx into cos raised to the power nx, where in the first case solving such a problem is going to break up into several different cases depending on whether m and n are even or odd. First of all, if power of sine is odd, the following substitution will be effective. Expand sine square as 1 minus cos squared. Then substitute u equals to cos of x. This will reduce the integrand to something that is easily computed. If likewise, if m is even and n is odd, if the power of cos is odd, then we'll apply a similar simplification, expand our cos function as 1 minus sine squared, and then substitute u equals to sine. The one remaining case is when both m and n are even. That means both of them are even. In this case, the substitution will not work. A reduction formula is required. A reduction formula like this is required. So, well, if we say that sine is odd, we can split off an even number of powers of sine. Like if we have sine raised to the power 5x, so the power of sine is odd, we can split it into sine raised to the power 4x into sine x. Okay, now integrals involving power of tangent and secant. Tangent and secant follows the same pattern depending on the parity of powers. If power of tan is odd, then perform the simplification expanding out every tangent squared as secant squared minus 1. Then substitute u equals to secant. Likewise, if n, the power of secant, is even, then one can simplify every secant squared is 1 plus tan squared. The substitution u equals to tangent will then work. Now, integrals of the form cot mx cosecant nx dx can be found by similar method because of the identity 1 plus cot square x equals to cosecant x. Now there is one last class of integrals that we are going to look at, and that is something in the form of integrals of sine of m theta and sine of or cos of n theta. So the sine and cos both have different arguments. So if we have something like that, sine of mx into sine of nx, we can solve them like 1 by 2 into cos of m minus n into x minus cos of m plus n into x. And if we have sine of mx into cos of nx, we can apply this expression 1 by 2 into sine of m minus nx plus sine of m plus nx. What it will simply um, convert your expression into the form uh, into those basically functions which are easier to integrate, whose integral you can easily solve. Well, you can say that why would any of these integrals be useful to you people? So one of the important reason it is that sine and cosine trigonometric functions pervade the physical universe. If you go far enough in mathematics, you will learn about the Fourier analysis, which is a mathematics built on sines and cosines, and it's extremely useful in analyzing any kind of wave, whether an electromagnetic wave. In fact, one could say that all the radar and signal processing is built on the basis of integrals of sines and cosines. So we should know them. We should know how to compute them quickly. So here is an example of integral sine of 3x into cos of 5x. Both are the trigonometric functions with different arguments. Now, which formula we can, this is basically an expression of this form, and we can apply sine of m minus nx plus sine of m plus nx. Here the value of m is 3 and the value of n is 5. So 3 minus 5 is minus 2, and m plus n, that is basically 3 plus 5, this is 8x. Now, what we'll do is we'll integrate this function sine of 8x and sine of 2x. So the integral of sine of 8x is minus cos of 8x by 8. 8 is multiplied with 2. So we get minus cos of 8x divided by 16 plus cos of 2x divided by 4 plus some constant of integration. So in this manner, we can integrate the expression in which there is a multiple of there is basically the product of two functions, trigonometric function sine and cos, having two different arguments. Now let's discuss the cases one by one. Integral of sine cube x into cos square x dx. Now here we can see it's the integrand is the product of two functions sine and cos, and the power of sine is odd. This means we are dealing with the first case. Now what we will do is we'll split it into two terms. As it is sine cube x, we can write it in the form of sine square x into sine x, and cos square x is here. Now, sine square x can be written as 1 minus cos square x. Cos square x is the same, and sine x dx can be written as minus d of cos x. Now, what we can do is we'll do substitution. Let u is equals to cos of x. If u is cos of x, then it is 1 minus u square, it will be u square, and this will be minus d of u. Now what we'll do is we'll multiply u square minus u4, and this negative sign will make it u4 minus u square du. We can solve this u4 and u square very easily. The integral of u4 is u5 by 5. Integral of u square is u cube by 3 plus some constant of integration. Now doing back substitution, u is cos, so cos raised to the power 5x by 5 minus cos cube x by 3 plus z. Now comes another example, cos raised to the power 5x. This is basically your case 2, because um, the power of cos is odd. Now what we can say is we can basically break it into cos 4x into cos x. Now cos 4x is equal, we can write cos 4x as cos square whole square. So cos square is equals to 1 minus sine square x, so 1 minus sine square x whole square into d of sine x. Let u is equals to sine x, so 1 minus u square whole square du, applying a minus b whole square formula, so it will give us 1 minus 2u square plus u4 du. Integrating this expression, we get u minus 2 by 3 u cube plus 1 by 5 into u5 plus some constant of integration. Now doing back substitution, we get this expression. Now it's very easy to solve these kind of functions. Now comes a definite integral under the radical 1 plus cos 4x dx. As we all know that cos square x is equal to 1 plus cos 2x divided by 2, and 1 plus cos 2x is equal to 2 cos square x. Now, we don't know what is cos 4x, but we can convert it. As we know that 1 plus cos 2 theta is equals to 2 cos square theta. If theta is equals to 2x, then 1 plus cos 4 theta is equal to 2 cos square 2 theta. So we can replace this whole expression by 2 cos square 2 theta. So replacing it with this expression, we get 2 cos square 2 theta 2x under the radical, and we know that under the radical x square is equals to mod of x. So I can write it as cos of 2x. Okay, now I can write it as cos of 2x dx. Cos of we can integrate cos of 2x, it is equals to sine of 2x by 2. Applying the limits, I get this expression. Now comes the integrals of powers of tan and secant. Here comes tan 4x into dx. We can split it into tan square x into tan square x. Tan square x can if tan square x is basically equals to secant square x minus 1. Multiplying it, we get tan square x into secant square x minus tan square x. Tan square x can be written as secant square x minus 1. As integral is a linear operator, we can apply it term by term. We can do some substitution, like u is equals to tan x, so the derivative of du is secant square x dx. It's the part of the integral, so we can write it as integral of u square du. So integral of u square du is 1 by 3 u cube plus some constant of integration. We know already the integral of secant square, that is basically tan x, and the derivative of integral of 1 is x plus some constant of integration. We have discussed this example. Now comes exercise 8.3, integral sine cube x into dx. As sine cube x, the power of sine is odd, so we can split it into two terms, sine square into sine x. Sine square x can be written as 1 minus cos square x. Multiplying it, we get sine x into cos square x into sine x. Now we can um, do integration. The integral of sine is minus cos. As we know that if derivative of a function is written in front of a function, then what we can do is we can increase the power of the original function and divide it by that power. So the derivative of cos is sine, it's written in front. Derivative of cos is minus sine, it's written in front of that function, so I can increase the power of cos by 1, so it's cos cube by 3 plus some constant of integration. Now comes another question, cos cube x dx. Cos cube x can be written as cos square x into cos x. um, Cos square x is equals to 1 minus sine square x into cos x. Multiplying uh, both of these, we get cos x into sine square x into cos x. Integral of cos x is sine x, and once again uh, we'll increase the power of sine by 1, so sine cube x by 3. Now comes another example, sine cube x into cos cube x. Here both of the trigonometric functions have odd power, so we'll select only one. Sine cube x will be written will remain the same, while splitting this cos cube into two terms, cos square into cos x. Cos square can be written as 1 minus sine x. Multiplying all the terms, we get this expression. Now increase the function, the power of the function by 1, so I get sine 4x by 4, and here I get sine 6x by 6, because um, the function's derivative is in front of the function, so I can increase the power by 1 divided by that particular power. It is also the same sine 7x. We can write sine 7x into sine 6x into sine y. Sine 6x can be written as 1 minus cos square whole cube, and we can solve it. Then comes another question. It's also simple, um, converting that, splitting this odd power into 2. Sine square 2 theta will remain the same. Cos cube 2 theta can be written as cos square 2 theta into cos 2 theta. So cos square 2 theta can be written as 1 minus sine square 2 theta into cos 2 theta d theta. Multiplying the expression, I get this, and integrating it, I get this expression. Here integration is not difficult, it is easy. Now comes another question, integral of 0 to pi under the radical 1 minus cos 2x dx. As we all know that 1 minus cos 2x is equals to sine square x. Um, so it's 2 sine square x. So I can write it as under the radical 2 into under the radical sine square x. As we all know that under the radical x squared is equals to mod of x. So I can write it as mod of sine x, and we know that on this particular domain this function is positive, so I can I can take the positive function uh, sine x. Now integrating sine x, I get minus cos x, and applying the limits, I get this answer. These questions are not difficult, these are easy. Now here we have secant raised to the power 4 3x into dx. We can write it as secant square into 3x into secant square into 3x. So secant square 3x can be written as 1 plus tan square 3x into secant square 3x into 3, this 3. Now multiplying the expression, I get this, and after integrating we get this answer. Same goes for cot 4. Cot 4 can be written as cot square into cot square. Cot square can be written as cosecant square minus 1. 8 is a constant, so we can write it outside the integral. Multiplying the expression, I get this. Integral of cosecant square t into cot square t is minus cot cube by 3, and cot square can be written as cosecant square minus 1. Integral of cosecant square is minus cot, and integral of 1 is t. So this is the answer. Well, it is not difficult. It's not difficult to solve these questions. Um, Once you'll understand the theory, once you'll remember the formulas, it will be difficult, it will be easy for you to solve all the questions. Now you can solve the questions of exercise 8.3 easily.